Alright, hi everyone. Today we're working on, again, rational functions. Rational functions. Yeah, rational functions. Rational functions. And that means another word of saying fractions. We already worked with keywords like horizontal asymptote and vertical asymptotes. We talked about how to graph them, and on your work, your practice, you guys went through graphing these vertical and horizontal asymptotes. And hopefully you guys are finding these to be quite easy, identifying what's your vertical asymptotes. Horizontal asymptotes, you just have to remember those three rules. Is the top exponent bigger? Whoops. Are they the same? Or is the bottom one bigger? Okay, these are the three rules. If the top is bigger, there is no horizontal asymptote. If they're the same exponent, we copy the front values in the front. That's horizontal asymptote. Here in this case is y is equal to 1 over 1. And if the bottom is bigger, see how the bottom is bigger here? That means we have a bigger bully on the bottom. Our horizontal asymptote was going to be y is equal to 0. Three simple rules. If you forget them, that's fine. You can make it up. If I say x is 10, right? What's 10 squared over 10 squared? That's 100 over 100. Hey, what's 100 divided by 100? It's 1. But if I say over here, what's 10 squared over 10 cubed? That's 100 over 1000, and that's a small number. Oops, that's 1 over 10. And as we get larger, if I say 100 squared over 100 cubed, the divide becomes even more. I think it becomes 2 now. So as x gets bigger, we get closer and closer. We get small numbers to 0. Okay. Pretty much the bottom blows the top out of the water. Now we had a new term today, and this is something that we kind of avoided, and that's holes. And holes are drawn specifically, and they're super easy to find. They're quite obvious. Now let me show you an example of a hole. And the problem is this: x squared plus 4x plus 4 divided by x squared minus 4. Okay? Now, if I go halfway through the problem and we look for vertical asymptotes first, we normally look for vertical asymptotes by factoring the bottom. So if we factor this, this would have been x squared plus 4x plus 4 divided by x plus 2 and x minus 2. Hopefully you guys are able to factor the difference of two squares. X squared plus minus 4 is equal to x plus 2 times x minus 2. All right, 2 times 2, x times x is x squared, 2 times 2 is negative 4, and then the plus 2 and minus 2 divide out. Cancel out. But I want to show you something, because we're claiming, here's the claim, and this is going to be a wrong claim, is that we have vertical asymptotes as x equals to negative 2 and positive 2. Negative 2 and positive 2. That's the claim. But I want to go ahead and graph this out right now. And I want to see, do we really have vertical asymptotes here? So I'm going to write x squared plus 4x plus 4. And we're going to parentheses divide this by x squared minus 4. Now again, we claim that we had a vertical asymptote at negative 2, x equals to negative 2, as well as x equaled, as well as x equals to positive 2. I want to change this slightly to, change this to be a dotted line here so we don't get too confused. Change it to blue. Alright, so you guys can see here that my claim is that we're supposed to have two vertical asymptotes. But we don't, do we? And I'm going to show you guys something real quick. Let me go ahead and get rid of the second asymptote here. We were supposed to have two. Oops, got rid of the wrong one. But we only have one. Now, why is that? And was this predictable? Why do we only have one when it looks like we should have had two? Now I want to show you something kind of interesting. Let's go back to the original problem here. And I'm going to go ahead and show you something interesting. And what's interesting is, you know what if I factor the top also? X plus 2 times x plus 2 over x plus 2 times x minus 2. I want you guys to see something that looks like twins. You'll notice that we have an x plus 2 and x plus 2. And in math, normally what happens when I'm dividing stuff that is exactly the same? They divide out to become 1. And this problem now looks like x plus 2 over x minus 2. Which of these graphs are easier to graph? The original x squared plus 4x plus 4 divided by x squared minus 4? Or do you think this one over here would be easier to graph? Well, I would claim that the second one, the simplified version, would be easier to graph. And that's the graph that we graphed. If you look back at what we graphed here, our vertical asymptotes, let's go ahead and take a look at some characteristics of this. The vertical asymptote is, for this problem, x equals to 2. My horizontal asymptote, take a look here. We both have a exponent of 1 here, 1 and 1. That means they're the same speed. So the horizontal asymptote, y is equal to 1 over 1, which is just 1. Let's go take a look at the graph that we graphed. And please take a look, as we mentioned before, we do have a horizontal asymptote at 1. That looks like kind of 1 to me. Let me go ahead and draw that one out. Y is equal to 1. Okay, you guys can see y is equal to 1. That looks like 1. That's what the graph eventually becomes. We do have a vertical asymptote at 2. Okay, so we have our graph. But this is wrong still. We have one point that's missing. And that's where our term, the whole, comes in. So I want you guys to look back here and look at the term that we canceled out. We canceled out the x plus 2. But in the original function, we weren't allowed. X could not be negative 2, could it? Right? That's negative 2 right here. And this is where our whole falls. And why do I call it a whole? Because one thing is, I'm not allowed to graph that point. That point does not exist on my graph. But do we still have to draw it? Yes, but let me show you how we're going to draw it here. If I look at the graph at x equals to 2, can you guys see the whole? Can you guys see that it doesn't exist at negative 2? Can you guys see that? Okay, take a look. Here we go. As I get closer to negative 2, boop, it disappears, doesn't it? See how it disappears? Why? Because the graph does not exist at negative 2. And what we do is we draw a hole there instead. So let's go ahead and redraw this graph without decimals here. We said our original graph has a horizontal asymptote at 1 and a vertical asymptote at 2. 1, 2, dot, 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 dot. Horizontal asymptote at 1, dot, 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 dot. And I'm going to right now graph the point that doesn't exist. We said x does not exist at negative 2, does it? We divide it out, it's gone. This is what we call a hole. So we have a hole at x equals negative 2. But the hole is a point. So that's figure out where the y value is. We plug it into my simplified version. Negative 2 plus 2 over negative 2 minus 2. In this case, that's 0 over negative 4, which is 0. My y value, my function, is going to be 0. So when x is negative 2, y is 0. Does the graph exist at negative 2? No, it doesn't. But what would it have looked like at negative 2? It would have looked like 1, 2, a hole. And that's how we graph holes. You might have seen this in Algebra 2. And this is an Algebra 2 scale. We're just recovering it again. So what we do is we draw a big O right there at negative 2, 2. And that is not a point on the graph. That is a point that we are going to cross on the graph. But we're going to almost like skip over that point. Now, I want us to ask ourselves this question. Is the graph going to be up here, down here, up here, down here? Well, one thing I can tell you, since we have to be skipping negative 2, 0, the graph must cross through this hole. That's a freebie right here. If I want to double check what the graph looks like on the right side, let's plug in 3. Okay, if I plug in 3, 3 plus 2 over 3 minus 2, that's 5 over 1. 1, 2, 3, 4, 5. We're up here. So we're graphing on the top part of the upper right and the lower left. This is a complete graph, including the hole. So how do we find holes? Holes are when the function itself divides out one of its factors, and that is the location of the hole. Okay, let's do another problem. As you guys are finishing up there, let me go ahead and set up the next problem. If I write f of x is equal to x squared plus 6x plus 8, and we're going to divide this by x squared, let's see, plus 5x plus 4. Okay. Now, I'm going to go ahead and first start off with this. Just pretend that this is a normal graph that we didn't even know there's a hole. And then we'll realize why we have to check. If I went ahead and factored the denominator looking for the vertical asymptotes, that's x plus 4 and x plus 1. Is everyone okay with the denominator being x plus 4 and x plus 1? So we're claiming normally x cannot be negative 4 and negative 1. Because if it was negative 4 and negative 1, we would be dividing by 0 and we would all go to hell. We have sinned greatly. No, it is undeterminate, so we're going to shoot off to infinity. So normally we would go ahead and start graphing the graph. We would do negative 1, 2, 3, 4, and negative 2. But I want to show you right now that that's not what the graph looks like. Because we're going to realize that one of these factors are going to cancel out. Now again, if I go ahead and try graphing this, you'll notice that we don't have 2 vertical asymptotes. We only have one. Let's go ahead and graph it at, let's plug in the equation. X squared plus 6x plus 8. Divide that by x squared plus 5x plus 4. Whoops. And you can see that we are missing one of our asymptotes. So this is going to be negative 1. Okay, so we do have vertical asymptote at negative 1, but we're missing our vertical asymptote at negative 4, right? I want to show you guys something kind of interesting. Let's go find 4. And as we get closer to 4, take a look, everyone. As we get closer to 4, we're getting closer. Oh, do you guys see it? Oh, do you guys see the hole? It's kind of hard to spot. It's like the Loch Ness Monster. It's there and it's not there. And that's the big deal here. Because at the hole, it's undefined. So here's something we know. If we have a hole, we know the top is going to be x plus 4. We know we're going to end up dividing that. And let's go ahead and factor the top. That's going to be the factor of x squared plus 6x plus 8 is x plus 4 and x plus 2. Now here's the big takeaway here. We know there's a hole. Fine. Perfect. That actually makes your life even easier. It makes the problem even easier. So what are we trying to say? Let me take a sidestep here and ask you, are these the same thing? If I ask you to say, is 10 divided by 2 the same as 5 over 1? Are they equivalent statements? Oh yeah. But why is that true? Because if I took out 10 and I said, isn't 10 2 times 5 over 2 times 1? Couldn't we say the 2's divide out? That's exactly what we're doing here. We're saying whatever term that would have been, that would have divided out. If x was 1, well, that's 5 divided by 5. If x was 2, that's 6 divided by 6. If x was 10, that's 14 divided by 14. They were always going to divide out. But is there any difference between 10 over 2 and 5 over 1? Numerically, no. So is there a difference between the graphs x squared plus 6x plus 8 versus x squared plus 5x plus 4? Is there any difference between these two graphs? Answer is almost. These are almost the same thing. And here is where we get lost. Is because we said originally that x can't be -4, right? And x can't be -1. Yes, on this graph here, x cannot be -1, but it also cannot be -4. It can't be either of these numbers. If you're trying to tell me these are equivalent graphs, you also have to skip -4, even though it canceled out. Yeah, even though it canceled out. But just because your parents aren't home doesn't mean you can have a party, right? Your parents aren't home, that means we can party, do whatever we want. Nope, the rules are still there. As if your parents were still there, you still have to follow these rules. And the rules are that we can't use -4. But at every other point, this graph looks just like that graph. So which graph should you graph? You graph the easy version. Every point is exactly the same, except at the hole. And that's how we're going to make this problem easier. Let's go ahead and graph the right one. We have a vertical asymptote only at -1. All right, here we go, -1, -1, ... How hard was that? Horizontal asymptote, take a look at the horizontal asymptotes. Do you have any numbers in front? That's 1 over 1. 1 over 1. That's 1. Okay, I'm halfway through the graph. Now we're going to look at some characteristics on the top. What was a 0? What number can I plug in to cancel out a +2? A -2. If x was -2, isn't x plus 2 equal to 0? Isn't x, if it was -2, this would become 0? Hey, -2 plus 2 is 0. Turns out at -1, -2, we have a 0 point automatically. Bam, easy peasy. Let's do another point. Let's find our y-intercept. If x was 0, what numbers are left? 2 and 1? That's right. 2 divided by 1 is 2. When x is 0, y is 2. We have another value here. We already have everything we need to graph this graph. We're going to be up here, and we're going to be down here. We took a complicated x squared graph, and we're just graphing a regular x graph now. But we have one more issue. In our original graph, we said we could not be at -1. Yes, you're right. We are not at -1. We have a vertical asymptote there. But also, you're not allowed to be at -4. And -4 is way over here, -1, 2, 3, 4. And you have to draw out the hole. Now, what would the hole be? Well, plug it in. Now, please be careful. If I plugged in -4 to my original equation, wouldn't we still be dividing by 0? So here is the gimmick. You don't plug in -4 to my original one. You plug it to the lookalike. You plug it here. You plug in -4 here. Let's go and take a look. What would -4 look like if it could exist? -4 plus 2 over -4 plus 1. What would the whole look like? It would look like -2 over -3. It would look like 2 over 3. This is what the y value would look like at x equals to -4. And let's follow the trend here. If you look at the graph here, we were going to cut through here and we were going to be up here someplace. Up here. It's in the positive section, isn't it? On top. And we would have to draw a hole at -4. Here's -4. Positive 2/3. That's our hole. So this graph, if I go ahead and graph it again, let's use a blue line now. We'd be going up, cross our 0, and head over to our hole. Now take a look. I made that hole pretty darn big. It's like a ripped pair of jeans that they charge you $80 for. So it's really obvious. So everyone can see it. And we have our line on the right here, heading toward the asymptotes. So how do you spot a hole? Well, I hope they factored for you, because if they do, the holes are super easy to spot. Now, one thing I need to say, when you find the hole, if they ask you what is the point, because a hole is a point, right? You have to give them the x and y point. If they just ask you where's the hole, just the x value, that's fine. You can leave it as an x value. Okay, as you just the front. Now, let's go ahead and take a look at your homework today. It is going to be a mix of us worrying about holes. Okay, first question here is, for what values of x does the rational function have blank? And we're going to fill in these blanks A and B. Okay, I'm going to go ahead and actually do two things here. I'm going to go ahead and copy this so I can write on it. Save PDF to files. Okay, so I'm going to write on the right side, and then I'm going to be able to plug in the answer on the left side to just verify it. Okay, so the first question is, for what values of x does the rational function have blank holes? Please take a look at this first question. Are there any holes in this? Do any of the factors cancel out? Would they have divided out naturally? 64? Nope, no 64 is on the bottom. 60? No 60 is on the bottom. So there are no holes here. And I'm going to write, plug in here, there is nothing. So they want you to write D and E. So if there are no holes, the tip on the trick here, they gave a tip, is write D and E. So I'm going to write D and E. Does not exist here. D and E, D and E. Right. What about vertical asymptotes? Looking at this problem, what are the vertical asymptotes of the problem? Do we look at the numerator or denominator for vertical asymptotes? Hopefully you remember we get vertical asymptote when we're dividing by 0. That's negative 43 and positive 20 and negative 13. That's how fast we could be writing this. Bam, those are my three numbers. Easy peasy. Now, I want to go back and say this. If our vertical asymptote was a hole, is it still a vertical asymptote? Answer is no. If our vertical asymptote was a hole, it is no longer a vertical asymptote. It's a hole now. Okay, let's look at our next problem here. Take a look. Are there any holes here? And this was a tricky one. Well, doesn't x minus 26 divide by x minus 26? But I have two of them, don't we? X plus 26 and x plus 26. We have two of them, so it only got rid of one of them. So in this case, yes, there's a hole, but there's also a vertical asymptote there. It's still there because we still can't be x minus 26 in my new graph either. So question number 2, is there a hole here? Trick question. It would have been, but I have too many x plus 26 on the bottom, so it still stays a vertical asymptote. And that might be a trick question for us. But it's both, Mr. Ko. Well, it's still a vertical asymptote in my new graph because we still have the x plus 26 there. My vertical asymptotes will be negative 26 and 39. All right, looking at the next problem. Does anything divide out here for this problem? Hopefully you guys can see. Yes, the x plus 2 and x plus 2 both divide out. Okay? So what is the hole here? The hole will happen at x equals to negative 2. This is where the hole is. That's the factor that divided out. Do we have a vertical asymptote? Yeah. This is what's left over. X plus 10 over x minus 4. We still have vertical asymptote at x equals to 4. Take a look at the answers. Negative 2 and 4. So once you wrap your head around this, it's actually a super easy, fast homework because you're looking to see, is there a vertical asymptote? Are there holes? What's left over after everyone fights? Is x plus 10 and x minus 10, are these guys going to divide out? They are not, because they are not exactly the same term. If I give you a number like 1, the top would be 11, the bottom would be negative 9. Does 11 and negative 9 cancel out? Nope. So plus and minus do matter. They have to be exactly the same term. So because nothing cancels out, do we have any holes? The answer is there are no holes here. So what do we have? We have a bunch of vertical asymptotes at 10 and negative 1. Our next problem here, do we have any vertical asymptotes here? Take a look. X minus 2, x plus 4, x minus 2, x plus 1. Hopefully you'll notice that these divide out, and when they divide out, we have a hole here. My new equation would have been x plus 4 and x plus 1. Does that look like my old equation? It's a simplified version. It's the easier version. The original one said you can't be 2 and you can't be negative 1. These are the x values that don't work. Well, we can now classify as negative 1 is a vertical asymptote, and we have a hole at 2. Hole at 2. Oops. A hole at 2. Come on. And a vertical asymptote at negative 1. So this could be a very fast problem. The problem is that you might forget what a hole is. And you have to remind yourself that if they divide out, we have to remember that that value still does not exist, even though it's simplified now. Okay, let's jump down. You guys have a bunch of these problems. And then here's the next type of question over here. Let's look at question number 11. Number 11 shows you a polynomial. So I did not factor it for you here. You have to factor it yourself now and make a judgment call yourself. If I can factor it, numbers that make up 6 are 6 and 1 and 2 and 3. 2 plus 3 is 5, so we know the factors are x plus 2, x plus 3. On the bottom, to make 12, it's 1, 12, 2, 6, 3, 4. And do any of these guys subtract out to become 4? Yes, 2 and 6. X, 2 and 6. I always write down the numbers first before I think about the signs. We need more negatives than positives. Perfect. This leads us to see that there are terms that are going to factor out. Sorry, going to divide out. And we have a hole at x equals to negative 2. That's where our hole is. Our leftover factors will be x plus 3 over x minus 6. We have a vertical asymptote at x equals to 6. Okay, so in some of these problems you have to factor yourself, and it makes the problem a lot easier. Now, from this step here, I can graph the original function very quickly if I had to. Vertical asymptote at 6. Horizontal asymptote. Take a look at the horizontal asymptote. Do we have one? Yes, we do. And the horizontal asymptote is going to be at 1. Horizontal asymptote at 1. Here's 1. Let's see, do we have any zeros? I can make the top go to 0. If x was negative 3, negative 1, 2, 3. We have a 0 here. Perfect. What about y-intercepts? Make those 0. That's negative 1/2. All right, negative 1/2. That kind of looks like it should have been there. You can see that this graph is going to be going in this direction. Where was my hole? Remember, we said we could not be at negative 2. My hole is actually at negative 2. If I plug it in, negative 2 plus 3 over negative 2 minus 6 is 1 over negative 8. This is a negative value at negative 2. Take a look here. My hole is right there. We have to make sure we get that hole in the right place. That's my hole. What does the graph look on the right? Since I have no information here, we have to now plug it in to my equation. Let's pick 7. So I'm going to plug it back into my easy version again. 7 plus 3 over 7 minus 6 is 10 over 1. So it's way up here. So we know we're stuck on the upper right-hand corner. So we have to be able to tell what the horizontal, the vertical, what the holes are, x-intercepts, y-intercepts. And if we still not enough points, we have to now plug in another point to figure out where this graph goes. Okay. Let's do one more. Let's do number 12. No, let's do number 13. Now 13 is asking everything about this graph. 13 says, the graph of f has a vertical asymptote where? Okay, where does it have a vertical asymptote? So if you look here, x minus 7 and x minus 7, they divide out. But it doesn't get rid of all of them. So we still have x minus 2, x minus 9, as well as x plus 7, x minus 2, and x plus 4. So where do I have vertical asymptotes? We set vertical asymptotes, and these are x values. X is equal to what? X is equal to negative 7, 2, and negative 4. The graph f has a hole on the coordinate. Do we have any holes in this problem? we would have, but we still had a vertical asymptote there. So instead of drawing a hole, you will just draw the vertical asymptote because it's stronger than that hole. So we have no vertical asymptotes. No, we have no holes. Okay. All right, that's it. Okay, someone brought up a point that I totally missed, the fact that 2 is actually a hole too. Oh my goodness, you're right. 2 is a hole. So we have a hole here. That's where the hole is. My goodness. Now, because you brought that up, 2 is a hole. That means it is not a vertical asymptote. So we're left with x minus 9 over x plus 7 and x plus 4. Thank you for catching that. I was so distracted by the x plus 7 there. So we do have vertical asymptote at negative 7 and negative 4. Now, they asked us to write it as a point. Okay, that means we need x and y point. So if we know the hole is at 2, x equals to 2, what's the y value? We're going to plug in 2, 2, and 2 into the problem. 2 minus 9 over 2 plus 7 over 2 plus 4. And that's negative 7 over 9 plus 6, which is negative 7 over, oh, times, I'm sorry, that's times. I don't know why I said plus. 54. So it's positive 2 comma negative 7 over 54. Thank you very much for catching that.